In this lab, we will talk about solve commands. We'll have few examples of for loops. We will also talk about multiplicities of zeros and limits at infinity. As usual, we will start with adding our normal libraries and a variable x for SymPy. In the first example, we start with the function sine of x squared, and the goal is to find its critical points. Since sine is a periodic function, we should expect to have infinitely many critical points, but as you will see later, it is very hard to find them. And so we start with defining our function, then finding its derivative. So our derivative is 2x cosine of x squared. And now we'll find critical points. So the first command we'll use is solveset. So I want to know when the derivative is 0. And as you can see, this is not exactly helpful. We see one of the critical points, it's 0, but the rest is not very readable. If you try to use simplify or n command, you will see it will not actually help you in any way. The second approach is we will use just a solve command. This is much better. We have 0 here, and we have 4 more answers. These are, of course, not all of the solutions, but at least it's more than before. Often, you will also need to graph your function or the graph of a derivative to make sure you have all the solutions. For example, let's graph the derivative in this case. As you can see, we do have infinitely many solutions, and the 5 solutions that we got here are in essence the one in the middle. And we can check this by using n command. So here's an interesting way to apply a for loop. I want to apply n command to every single thing in this list. So this is a list with 5 elements here. So what we will do, we will use a for loop. So for s in this list, that's the solve list, we will apply n command to every s, and then the brackets outside means my output will also be a list. And this is what it will look like. So this is my 0, and these are the other 4 critical points. So now by looking at the graph, you can confirm that the 5 solutions we got are the middle 5 solutions. And we can't really get the rest of it. The only way really to get the rest of it is to maybe use nsolve command. But remember, it will only give you one of the solutions each time. So you would have to use it together with the graph to figure out which solutions you are getting. Now let's look at another example with solve commands. This time I want to find zeros of this quinting polynomial. If I apply a solveset command to it, I do not get clear solutions. However, whenever you see CRootOf commands, this means you can always apply n command to estimate it in decimal form. This will usually happen for complicated polynomials or rational functions. So if I apply n command in this case, as you can see, we get much nicer solutions. Moreover, if we look carefully at what we have here, you can see that the last 2 solutions are complex. Since in calculus we usually only care about real solution, we can add a little argument here, domain equals sp.s.reals, to only show us real solutions. And as you can see, we have 3 real zeros. In the third example, we will look at multiplicities of zeros. You should be already familiar with multiplicities of zeros of polynomials. However, in this case, we will generalize it to any function. We define it as follows. X equals c is a zero of multiplicity m of f of x if a limit as x approaches to c of f of x over x minus c to the power m exists and does not equal to 0. For example, if I have a function sine of x, it has a 0 at 0. We know that the limit as x approaches to 0 of sine of x over x is 1, which means it exists and does not equal to 0. And therefore, x equals 0 is a 0 of f of x with multiplicity 1. Let's look at another example. Let's say we have f of x equals e to the negative x squared minus 1. This function is 0 when x is 0. So we want to know what's the multiplicity of it. We will check first if it's a multiplicity 1. So we take a limit f of x over x as x approaches to 0. We see that the limit equals to 0, and therefore the multiplicity is not 1. Let's check if it's 2. So now I take the same limit, but I have inside f divided by x squared. In this case, the limit equals to minus 1. So it exists and it does not equal to 0. And therefore, x equals 0 is a 0 of my function with multiplicity 2. As you can imagine, this may take a few tries. To speed up this process, we can create a for loop that will check all the multiplicities starting with 1 going up until it's find first non-zero limit. Here's an example. So for n in range from 1 to 11, so we will check multiplicity starting with 1 going up to 10, including 10. We find a limit of f over x to the power n as x approaches to 0. So we are checking whether 0 has specific multiplicity here. If this limit does not equal to 0, which means we found it, we will print the multiplicity is n. And this command break will stop the for loop, so we don't have to check everything else. So for example, in our case, the f has multiplicity 2, which we already knew. A small note here. We are assuming a couple of things with this for loop. The main thing that we are assuming is that our multiplicity is actually an integer. Technically, it doesn't have to be. However, in every single example you will have, it will be an integer, and therefore this will be enough. The second thing, I am assuming that it will be between 1 and 10, and again, we can always increase our upper limit here if we need to, but in all your examples, it will be between 1 and 10. Finally, we can look at this multiplicity graphically as well. So if I draw a graph here, you can see that the f of x touches x-axis at 0. So it looks like the multiplicity is even, and that's exactly what we got. And in our final example, we will look at limits at infinity. It is very similar to just normal limits. All we have to do is specify how to make x approach to infinity. And SymPy has infinity command. It's sp.oo. This is two lowercase o's. This means infinity. So this first limit is a limit of f of x as x approaches to infinity. If I want to approach to negative infinity, I just have to put a negative in front of my infinity command. And there we have it. Now for the assignment. The Lab4 assignment will consist of 4 problems. The first 2 problems will be about finding extrema, maximums and minimums, inflection points, and end behavior. You need to know how to find them. You need to know how to plot your function. The problem number 3 will be about mean value theorem. Here you have to know how to find tangent lines, secant lines, and how to plot multiple functions on the same plot. Finally, the 4th problem will be about finding multiplicities. You will be given multiple different functions and will be asked to find multiplicities of given 0 for those functions.